Is Guo Chuan Thiang from Peking University, because we have a wide audience here. Just to briefly introduce him, so Guo Chuan in particular has been worked a lot on sort of mathematical methods of topological insulators and semimetals, and sort of applying K-theoretic techniques and duality and sort of ideas about duality. But today he's going to talk about mathematical tools for anomalous boundary metals. So please, Guo Chuan, go ahead.
Right. Thank you, Chris, and thank you for whoever has turned up at this odd hour. It's fine on the east side of the world where I'm at, but I'm not so sure about the rest of the world. So I looked through the aims of this workshop, and I think we're supposed to kind of exchange some ideas from our own little corners of this mathematical physics. So hopefully my talk will fulfill this lofty aim, at least a little bit of it. So coming in some sense from insulators, but not quite, because the part of the point of the whole subject of topological insulators is that they're studied not in some infinite bulk limit, but when you introduce a boundary, it somehow turns metallic on the boundary. So in some sense, they're really interesting because they're very strange sorts of metals. Okay, so I'll try to explain this in more detail. I should watch the time because of a bit of a tendency to go over, and I believe it's half an hour, so I stop. Yeah,
it's a half an hour talk, if
half an hour,
but okay. Maybe with a little bit of leeway.
Minus 2 minutes that I've already spent. Okay, right. So since this is about conductors and metals, we're dealing with charge things. So electrons, these are fermions, and there's always a little bit of tension between whether one works in the single particle situation or in a many-body setting. Even in a so-called non-interacting regime, it's not quite clear that they are totally equivalent points of view, depending on what you want to do. So you need to be careful. And so let me remind everyone on how the Fermi sea is formed. So the idea of the Fermi sea is that you've got some single particle Hamiltonian acts on a Hilbert space, and you want to split the Hilbert space into two pieces. So you've got V, the Hilbert space V, with a spectral gap. So let's say there's an interval mu minus epsilon to mu plus epsilon. So mu is the so-called Fermi level. Then your Hilbert space splits into the positive energy parts, which I write as V sub plus mu, and the negative energy parts, which are V sub minus mu. So here's a little picture, and the situation arises when the negative energy states are infinite dimensional. Okay. But I also want to mention the situation where you may have some sort of discrete spectrum, as well as a continuous spectrum. Okay. So there are little blocks of spectrum, and there are also little dots of spectrum. So when you put a Fermi sea, you want to create a vacuum in the many-body Fock space, which is such that the negative energy states on the left-hand side are turned into positive energy states, and crucially, they have the opposite charge. Okay. So formally, what you do is you instead of V, you convert to a Hilbert space W with reference to the vacuum level mu. Sorry, is there a question? If not, I'll continue. And you pass from the negative energy subspace to its dual. So that's what the star in V sub minus comma mu means. Okay? And then you replace the single particle Hamiltonian to a positive Hamiltonian on this W sub mu. Okay? So on the negative energy states, you now put a minus sign in front of the energy, and you do nothing for the positive energy states. Okay? So everything that used to be negative energy now is positive energy with respect to mu, and then it has a complex conjugation by passing to the dual. Okay? So it has the opposite charge. After you've done this, then you can do everything functorially. You throw in the exterior power functor, and then you have the Fock space, And the vacuum line is, of course, just the zero exterior power. It's just a complex line. And that, by construction, has zero energy. And because of the spectral gap assumption, the next excited, all the excitations have strictly positive energy. Okay, so this is a gap ground state. Okay, fine. But what happens when you want to change the vacuum level? And in fact, this happens very often. If you change the vacuum level, so you switch to a different level, nu, which lies in a different spectral gap. Okay, so let's say in this picture, mu used to be on the left side here, and then nu is, let's say, 3 states higher up. Then what you used to call a filled Fermi sea will now be a state with 3 holes. Okay, so it's not. So it's when you change the vacuum level, you produce some holes in this case. Okay. So what happens is that with respect to nu, the decomposition has changed into positive and negative energy states. Okay. So the particular bit that has changed is the status of all the states that lie with energies lying between mu and nu. Okay. So you have to be careful of what happens to v sub mu nu, and you convert it to the whole states, the dual, when you change the vacuum level. Now, this is not so serious in the sense that at the level of the Fock space, there's a canonical isomorphism between the exterior power, so the sub Fock space for this v sub mu nu, and the v sub mu nu star. Okay. So the dual, the cave exterior power of the dual, is canonically isomorphic to the complementary, so the top dimension minus k, the exterior power raised to that level of the original finite dimensional subspace v sub mu nu. Okay, it's canonical up to a phase, and the way you do this is to contract it with a choice of a determinant in the top exterior power of v mu nu. Okay, so you take a completely filled state and then you contract it with this dual. So in practice, physically, what happens is if with respect to mu, you had 1 filled state and two unfilled states, okay, in this regime of where you're switching the vacuum level. Then when you switch the vacuum level to nu, what happens is you now have 2 holes. Okay. So if you have n filled states initially, then upon changing the vacuum level, you now acquire, you've changed that picture into a situation when you have n minus k holes. Okay, so keep that in mind. Later on, I'll come back to this. Now, this is usually not a problem, but you have a problem or an anomaly when you have a continuous family of such a situation. So suppose you have a continuous family of Hamiltonians as parametrized by topological space X. So you've got a map from K to H of K. Okay. So I use K here because K is usually the symbol used for quasi-momentum space in examples which come from solid-state physics. But such situations arise when people were studying gauge anomalies as well. Then the parameter space was actually the moduli space. So it's the space of gauge orbits of some gauge theory. More in other settings, it may just be some control parameters in your system. And in situations where you have boundaries, X may be a parameter space which labels the boundary conditions. So there are many situations in which you might have such a continuous family. Now, if you do have your Fermi level lying in a common spectral gap for all operators in this family, then the subspaces which are positive energy and the subspaces which are negative energy, they vary continuously. Okay, so there are no jumps, and then you can make good sense of these creation and annihilation operators localized in the parameter space at value k. Okay, so this is what you usually do in solid-state physics. So strictly speaking, you should smear these things out by some function on X. Okay, but nevertheless, you can make good sense of this, although there are some caveats. But now you notice that even if each individual HK is gapped, it may be impossible to find a common spectral gap for the entire family. And this impossibility is not something which is spurious. It's impossible due to some obstruction, okay, due to something which I like to call topologically protected gaplessness. And in general, when you have this sort of protected obstruction, you would expect there to be some cohomology class which characterizes such an obstruction. So this is a perturbation-resistant boundary signature of a topological insulator or semimetal. And this is typically where the examples arise from solid-state physics, but actually many other examples abound. So let's recall the notion of topological insulators and their H states. So I'm actually not going to work in the bulk picture. I'm going to work in a picture where you have a half space operator. So most of the time you deal with in solid state physics, some periodic translation invariant bulk Hamiltonian. Okay, it's local, so it has a finite range hopping terms. And let's say it's in d-dimensional space, and it has a spectral gap between energy levels B and C. Then in the band theory, you usually have a spectrum which disperses into discrete energy bands as parametrized by the Brillouin torus of D dimension. So here's an example of the dispersion relation. But if you work on a half space, then only the momentum parallel to the boundary of the half space is conserved. And what happens to the energy dispersion with respect to the missing unconserved momentum? Well, it's collapsed into the essential spectrum. Okay. So instead of a little discrete band, discrete energy bands, you have thickened bands, become solid bands. And you have for each quasi-momentum parallel to the boundary, you have a Fredholm operator. So what might happen is that you acquire some discrete spectrum in between these essential spectrum. And a little theorem, and there are many accounts of this depending on your assumptions. But the general idea is that if in 2 dimensions you have what's called a Chern insulator, and this means that in the band picture you have your valence band comprises a line bundle of eigenstates, which has a non-trivial Chern class. Okay. Then when you pass to the picture with a boundary, so you have these solid bands, then the discrete spectrum actually arises in a funny way, and it must flow across the gap. So you must have a spectral flow from the lower energy bands to the upper energy band. Okay, so that's a kind of analytic, but where's the topology? Well, it's a little bit in the spirit of index theory, but it's not in the sense of index theory of a single operator. We all know that self-adjoint operators have a trivial index. The self-adjoint Fredholm operators have trivial index, but so it looks boring. But the space of self-adjoint Fredholm operators has non-trivial loops. Right? So in particular, Thiang and Singer showed that if you look just abstractly at the topology of the space of self-adjoint Fredholm operators, then its fundamental group is isomorphic to the integers. Okay, and its third homotopy groups, fifth homotopy groups, and so on, they're all isomorphic to the integers. Okay. This is a bit abstract, but concretely in the n equals to 1, this is just the spectral flow, which we already saw in the case of the Chern insulator on a half space. To make it precise in such a way that it's actually a topological invariant, you may use the definition of Phillips in 96. Now, the point behind this sort of abstract analysis is that actually your real operator would not have spectrum that looks so nice. It may be perturbed. Okay, so I give you a very nice picture of spectral flow just now, maybe in an exactly solved Toyn model, but in practice, the perturbations might make it look very complicated. Okay, but the point is that whatever the perturbations, you can control the class of perturbations which conserve the spectral flow by the topological invariance of the spectral flow. Okay. Now, I want to talk about unbounded operators, and the spectral flow originally arose, at least in the physics context, for operators with compact resolvent. So these would be, for example, Dirac operators on compact manifolds. And we saw some examples yesterday on of Laplacians, for example, on minimal surfaces with or without boundary. In that situation, the spectrum is discrete. So to study spectral flow, one usually cheats a little bit and just takes the bounded transform. Okay, so you take the operator h and divide it by square root of 1 plus h squared. And what this does is just to flatten all the big eigenvalues to plus and minus 1, which now become accumulation points of your eigenvalues. Now, generally speaking, we do not have this compact resolvent, and we still want to make sense of topologically invariant spectral flow. So really, technically, we should work with some sort of unbounded operator topology. And some examples that work are the gap topology. So this is the topology of convergence of the resolvent in norm. Okay, or you can even weaken it further to what's called the Weyl topology. So I don't have time to go through what these topologies are, but just to rest assured that you can make homotopy invariant sense of spectral flow for unbounded families of self-adjoint Fredholm operators. Right. So the key conceptual point is that the presence of essential spectrum, or in other words, infinite reservoirs of eigenvalues, allow for the situation when a Fermi surface is topologically non-trivial. Okay. So in this simplest example, the Fermi surfaces at a particular energy is just a point. Okay, but it's not just a point; it's a point with a sign, depending on how the eigenvalue is flowing across it. If you don't have the infinite reservoir, then what goes up must always go down. Okay, so you have 2 points in a Fermi surface with opposite signs, and in some sense, its homology class is trivial. Okay. So they're interesting in a homological sense, which is dual to this so-called cohomology obstruction, which I alluded to earlier on. And having these infinite reservoirs above and below the Fermi level allows for such anomalous Fermi surfaces to form. Let's see some concrete examples which arise, for instance, for Weyl semimetals. Let's see. So I've already gone halfway, and should check that I haven't lost the connection and everyone's still following. Are there any questions for me at this point? Sorry. Right. Okay. After no questions, I'll go through an example of a non-trivial spectral flow for these unbounded operators which do not have a compact resolvent. And the basic example just comes from Dirac operators, or massive Dirac operators. If you consider it on a half line, this is the Dirac operator on a half line. So it has the derivative part, and then it has the off-diagonal mass term, which anti-commutes with the derivative operator, the first order derivative operator along the diagonal. On a half line, you have to introduce some boundary condition to make the problem self-adjoint. And it's quite easy to show that the boundary condition is parametrized by the phase shift that you get upon reflection at the boundary. So at the boundary of the half line, which we set to be at the origin, the second component of your wave function should have the same amplitude as the first component. Okay. Now, if you run through this family of self-adjoint Dirac operators, you find that, of course, the essential spectrum doesn't change. It's the usual spectrum of the Dirac operator with a mass gap. Right. But for half of the values of the boundary conditions, you have an eigenvalue, and the eigenvalue actually flows from the negative energy states to the positive energy. You can solve for it exactly. So this is actually a loop of unbounded self-adjoint Fredholm operators, which generates the fundamental group of the self-adjoint Fredholm operators. Here I mentioned that instead of, you can also fix a boundary condition and then vary the mass term as a complex mass term. So you have m times e to the I gamma as the mass term, instead of the phase appearing in the boundary condition. Now, the way this arises in Weyl semimetals is that for the Weyl semimetal in 3 dimensions, the Hamiltonian, at least close to a crossing point, is nothing other than the Dirac operator in 3 dimensions. Okay, so it's the Clifford algebra generators. So in this case, it's the Pauli matrices dotted into the gradient operator. So that's the Weyl Hamiltonian, and but if you consider it on a half space in 3 dimensions, then you can only Fourier transform with respect to the momentum, the translations along the boundary. And the Fourier transform just turns out to produce the family which we've seen earlier on in the previous slide. And so it's a family of massive Dirac operators parameterized by a complex mass term. Okay. And this is a Fredholm family everywhere except at the origin where the mass gap closes. So it has an opportunity to have some non-trivial windings because we lose the Fredholm property at the origin. And in fact, our computation earlier on, so this is a picture we saw earlier on, precisely shows that you do have a non-trivial Fredholm loop. And the presence of the spectral flow means that for each loop, you have a contribution to the Fermi surface. You have one point contributing to the Fermi surface. Okay, so as you vary the loop, you have this Fermi arc, which appears in the boundary momentum space. Of course, this is an idealized situation, and in practice, you have perturbations which you actually can't even write down exactly. You may qualitatively know what these perturbations are, but you can't really write them out for a particular experiment, for example. So you expect the geometry of this Fermi arc to be very complicated. So it may bend, it may bifurcate, so it may not be a smooth manifold, for instance. And the angle at which it comes out from this so-called crossing point may depend sensitively on the perturbations and the boundary conditions. But you can never get rid of it, okay, because of the topological protection via the spectral flow. And this is why when people try to find the experiments in very for which the model is very somehow quite naive, they're able to succeed because you don't have to be very precise about these things, and you can still find the Fermi arc. Okay. And this is the power of the topological argument. Okay. Maybe I'll skip this slide. This is just another example where the usual Laughlin argument is actually an example of spectral flow, in a sense which you can make precise. I actually want to go to reach the part where you have a new tool. Okay. Spectral flow, maybe it's known to many experts, but something which is not quite known, I think, is the concept of a gerbe. So to get to the gerbe situation, I will first re-explain what spectral flow is from the Czech point of view, the Czech cohomology point of view. And in terms of the story that I told you at the beginning of the talk, with these switching vacuum levels. So suppose you have a family of self-adjoint Fredholm operators, and they share some common essential spectral gap. So each of these operators may have some discrete spectrum inside this gap. Okay. But there may not be a global vacuum level that can be applied to all members of this family. So how do you capture the situation where you can't have a global gap? Well, you pick any candidate vacuum level mu inside this essential spectral gap. Then you define the open set, which is a subset of X, such that mu doesn't lie in the spectrum of H of K. Okay. So this is the maximal subset on which the candidate vacuum level mu makes sense. So if you want to take on this subset, you can say, okay, I can also try to change the vacuum to nu. And so on the intersection of u sub mu and u sub nu, you have two options, mu or nu, okay, in the vacuum. And then you have this transition function, which captures this dimension of the eigenspace which lies between energy levels mu and nu. So you have on all the double intersections, you have a an integer value transition function between these vacuum levels. This is nothing but a Czech one cocycle in terms of Czech cohomology, and it has a cohomology class in the first cohomology of X. So X doesn't. So the first cohomology of X is just all the homomorphisms from the loops into the integers. So for each loop in X, you can count the spectral flow along that loop, and this information is exactly the cohomology class, and the data specifying the cohomology class is this Czech one cocycle of these transition functions. So that's spectral flow from a Czech point of view. Now, if there is a global spectral gap, then the spectral flow is zero because the Czech cocycle will trivialize. Because this, you can find a global vacuum level. So your open cover comprises only one set, and by definition, the Czech cocycle is trivial. So you might think the converse is might be true as well. If you find that you have no spectral flow, then you have a global spectral gap, and you have a global vacuum. That makes sense. Actually, this is false, and this is where the gerb comes in. Okay. So remember that when I discussed earlier on in my talk about how to transition between two different vacuum levels, between which lie a finite number of energy states. The transition is not just the counting of the number of states that lie between. Okay? It actually depends on the choice of the determinant. So what you have is a determinant line bundle on the double overlaps. Okay, so you have a transition line bundle between different choices of vacuums. Okay? And these transition line bundles satisfy a consistency condition on triple overlaps. That is to say, there's a canonical isomorphism on triple overlaps between the transition functions, transition line bundle associated to a pair of vacuum levels, and that associated to a second pair of vacuum levels. And there's an isomorphism from these, the tensor product of these line bundles to the line bundle that's associated to the pair mu psi. So if you have three candidate vacuum levels, there's a kind of associativity condition for consistency. If you know something about gerbes, this is precisely the check data for what's called a bundle gerb. And this is a check co-cycle, and its cohomology class is called the Dixmuir duality invariant, and it's an element of the third cohomology group of X. So for instance, if X is a 3-sphere, then the spectral gerb construction as above, okay, can actually give an isomorphism from the third homotopy group of the self-adjoint Fredholm operators to the third cohomology group of the 3-sphere. Okay, so you start from a family, a 3-sphere family of self-adjoint Fredholm operators, and there exists some family which realizes this generator, and when you construct the spectral gerb, the Dixmuir duality invariant of that spectral gerb is non-trivial. And concretely, you can get this from the SU2 version of the Weyl semimetal that I described just now. Okay. The caveat is that you need to do it in 5 dimensions, on a 5-dimensional half space. Okay. But I want to point out that we had some discussion on Fermi surfaces, but the Fermi surface, if you look at this example that I've not written down concretely, but if you work it out, you'll find that the Fermi surface as a set or as a topological space depends very, very sensitively on the boundary condition and also on the choice of Fermi level. So you could develop from an arc, you could turn into a hypersurface, which looks completely different from an arc, and so on. So it's not enough in this business to consider these anomalous Fermi surfaces as a subset, as a homology class, etc. You need a much more sophisticated topological invariant, which actually takes care of the entire development of the Fermi surface as it interpolates across different Fermi levels from a lower essential spectrum to the upper essential spectrum. So you need a geometric object which actually captures the entire spectral interpolation for this family of operators. Okay. So for those of you who do a bit of high energy physics or string theory, you might recognize this as a kind of a story in what's called the Faddeev-Michelson anomaly. And so it is well known that projectively the Fock space bundle is well defined. Okay, so the choice of the vacuum level, although it modifies the Fock space, it modifies it up to something which is controlled by a determinant line bundle. So up to a local phase. So projectively, the Fock space bundle is well defined. But the problem is you can't lift this projective Fock space bundle to a genuine Hilbert bundle. And the obstruction is precisely this Dixmuir duality obstruction that I pointed out earlier on. And all this sounds very abstract, but I would convince you that we've already seen it in experiments. And we've seen it in none other than the time reversal invariant topological insulators, which kickstarted the entire field of topological insulators. And in that situation, there's an extra ingredient, which is very important, which is that of the fermionic time reversal. And what fermionic time reversal does is it reverses momentum. So if you have momentum k, a state in momentum k becomes a state with momentum minus k. And importantly, it's not an involution, it's squares to -1. And it was discovered by Fouquet Millet in the mid-2000s that the T invariant, time reversal invariant topological, time reversal invariant insulators are classified by a mod 2 topological invariant of the band structure. Okay. And a way to make this precise is to use techniques of K-theory, and this was worked by Giuseppe and my collaborator Kiyonori Gomi in 2016. These are abstract invariants, and usually by invoking a kind of bulk boundary correspondence, people say, okay, you expect to see these Kramer's pair or Dirac cones at the in the spectrum of when you cut the sample into a half space. So you look at the time reversal invariant momentum on the boundary Fermi surface, and then you look for these signature Dirac cone dispersions. And this is the picture from the experiments, for example. And this is the Kramer's pair of H states, or H state dispersion, to be more precise. So the only thing is I want to point out is that this naive counting is not quite an invariant, as you can see from the deformation of the Dirac cones. So you can shift the position of the Dirac cone, kind of discontinuously. You can also make it disappear into the essential spectrum, into the bulk spectrum. So it's not such a problem in low dimensions, but in 3 dimensions where you have to disperse over a two-dimensional boundary Brillouin zone, then you might think you have to find a Dirac cone that looks like this picture on the left. Okay, but actually, this picture on the right is topologically equivalent to this picture on the left, and the one on the right is not really a cone. Okay, but it has some interpolation, spectral interpolation, and it's unbroken. So in all these examples, what is conserved is some sort of equivariant spectral flow, but in a very a more subtle sense. And the precise way to make this spectral interpolation a conserved quantity is to construct a so-called real structure onto the spectral gerbe, which I explained earlier on. And interestingly, the idea of spectral gerbes actually was studied. Real gerbes was studied independently by string theorists in mathematics of oriented folks in string theory. Now the point now is with this extra real structure coming from the time reversal invariance, these spectral gerbe cohomology invariants can actually be non-trivial in low dimensions, and they're indeed exactly realized by the topological insulators on a half space. Okay. So these invariants exactly capture the spectral interpolation of the H states of time reversal invariant topological insulators. Okay. So rather than the Dirac cones, which is not quite precise, you should look at this higher spectral flow as the topological invariant. So today, I think it's a non-commutative day, supposedly. So I would like to say there's a non-commutative version of everything I've said. Okay. So if you have complaints about broken translation invariance, magnetic fields, disorder, perturbations in the geometry, etc., I'd like to advertise a point of view which uses coarse index theory. So you can look at some of the authors and references. And these build on the ideas of using C-star algebra and their K-theoretic invariants to study topological aspects of spectral features of solid-state systems. Okay. Did I go over time? Yeah. Okay. I think this is fine. Yeah. Thank you.
Okay. Thanks very much, Guo Chuan.
Okay.